Hi, my name is Dan Chitwood, and I'm an assistant professor at Michigan State University in the departments of horticulture and computational mathematics, science, and engineering. Welcome to the fourth video tutorial of Plants and Python. In this video, we'll be learning about loops and how to use loops to calculate the Fibonacci sequence. The Python learning objectives for this video are to learn about the range function and how it produces a series of integers to iterate over in a loop, how to write a for loop, how to use the plus equal sign as a counter in a loop, how to create an empty list outside of a loop and fill it with loop outputs, how to use a for loop to calculate the Fibonacci sequence, and how to write a while loop using a counter. The plant learning objectives are that plants are computers too. They iteratively produce outputs like leaves and flowers, just like loops. Modeling tries to recapitulate phenomena in nature, and no model is perfect. And the golden angle that plants use, and we will calculate in that later activity, is based on computational mathematics. We will be using sunflowers and the golden angle as inspiration to learn from plants in the next lesson and activity. So let's get started. We'll start with the range function and how it's used to produce a series of integers that we iterate over in a loop. This is a good time to go over the help function. If you're ever in doubt about what a function is, you can just write a question mark in front of it. If we hit Shift Enter, we see we get a little help box. It's not necessarily so helpful, but it will try to tell you something. So for example, we can see that the inputs to the range function are start, stop, and step. This is a lot like indexing and slicing that you learned about before. And it says it returns an object that produces a sequence of integers from start inclusive to stop exclusive by step. And this almost sounds exactly like indexing and slicing that you learned about before. So based on that, let's try to execute a range function. Let's put in the number 8. Maybe based on our indexing before, you would expect it to give you back 0, 1, 2, 3, 4, 5, 6, 7. And that's not what it gives us. Instead, it just gives us range 0 to 8, which is kind of what we would expect based on just putting 8 there. And so this is a little unexpected. So let's explore more. And as you'll see, range only works really in the context of a loop. And writing loops is easy. Writing loops is also powerful. So for a for loop, you just write the first line. It's very important to write this line exactly with the syntax as it's given here. You always start with for, and then you create a variable. We often use I, kind of like an index that you've used before, but you can call this variable anything you want. So we say for I in, and then we usually have either a sequence of integers that can be produced by the range function, or we can even put in a list. And the idea here is that we're saying for I in range or a list, and we're going to iterate over the list or the range function. This is important too. You need to end with a colon on the first line of your for loop. So you say for I in range, up to a certain number, let's say 8, and colon. Next, if you press enter after this line, you're going to see that your code will now be indented. This is another important piece of syntax in writing a for loop. The code within the for loop needs to be indented. Within the for loop, as you'll see, you can put anything that you want. The sky is the limit. Your code goes in the for loop. And what the loop will do is we're going to iterate over values of I. So what that means is for I in, and the first value of range is going to be 0. So I is going to be set to 0. Any code you put in here using the variable I will be processed using I equals 0. After the loop completes with your code, we're going to go back up again, and I is going to be assigned the second value, which will be 1. And then when I is 1, we'll go through the code again, go back up, start the loop again. Next is I equals 2, and we're going to keep on doing the loop for all the elements in range or a list, as you'll see later. So if we execute this, pressing Shift Enter, You can see we're printing I with each iteration. I is initially 0, so it prints 0. Then I goes to 1, it prints 1, and it goes all the way up to 7. So in this context, we can see what the function of range is. It's to produce a series of integers that we can iterate over in a for loop. Remember that the range function is just like slicing and indexing, as you learned before. It has a start value, an end value, and a step value. Remember always that in Python that the start is inclusive. For example, this is going to start at -8. It's going to go up to, but not including 10. And it's going to do it in steps of 2. So if we say for I in this sequence of numbers, it's going to start with I being the first start, because that's inclusive, to -8. And so the first number that's printed with printing I should be -8. They'll go back up, do a second iteration. If we're doing step 2, the next value of I should be -6, and we should get a -6. It probably should go all the way up to 8, but not 10, because it's going to go up to 10, but not including 10. So the last number with a step of 2 should be 8. So let's see what we get for the function. And indeed, we start at -8. We have steps of 2 going all the way up to, but not including 10. So the last number is 8. And basically what's happening is that we're starting with the first value in range, -8. We process all the code within the for loop. Right now it's very simple. It's just a print statement. We go back up, go to the next value in range, which is -6, process all the code, go back again. The next value is -4, and we keep on going to the end, which is 8. You'll notice that I put this comment here, is that always use the print function. And the reason is as you'll see when your code gets more complicated that you put in here, it'll just be good to see that the loop is running. It's good just to print I to make sure that the loop is actually processing. So that's your first for loop, the simplest for loop. Let's look at more tricks that we can use with for loops, including a += sign as a counter. So you can put a variable, or as you'll see very soon, even a list, outside of a loop. You can then run your loop and you can modify the variable outside of the loop. And so the variable will be continually updated as it's modified every single time the loop runs. Something very common is to create a counter. So for example, if you create a variable, let's call it count up, and you set it initially to 0, if you run your loop, you could, for example, add I to the counter, count up, every single time the loop runs, so that every single time the loop runs, I is going to be added to the counter. So the value of I is going to change. Even though it's initially set at 0, notice that you set it to 0 outside of the loop. Then when you do your loop, the counter is going to be modified, and it's basically ignoring what that initial value was. So we can constantly modify the value of the counter as the loop runs. This is a little bit of trickery with respect to math, because this is not a mathematically true statement, but it's important to know how it works. For example, here we have a range function starting at 0, going to 12 in steps of 2. So this will go 0, 2, 4, 6, 8. The counter is initially set at 0. And so in the first time the loop runs, it will be 0, and then I is going to be 0. So count up will be set to 0 again. In the second iteration, count up is still 0, but now I will be 2. So count up is still 0, but now I is 2, and so count up becomes 2. We run the loop again, it will be 4 then. Now count up is 2, and we're going to add 4 to it, and so now it will be 6. So basically this is saying whatever the counter was before, we're going to modify it with I, and we're going to reset it to that new value by adding I to it. And we're going to put in this for loop a statement where we print both I as well as the count up value so we can track what the loop is doing. And so you can see for range 0 through 12, step 2, it goes 0, 2, 4, 6, 8, 10, as we would expect. These are the values of I. Count up is initially 0. Then we add 0 to 0, and we're still at 0. But then in the next iteration, I is set to 2. So I was 0, we add 2 to it, and now the counter is 2. In the next iteration, the counter is at 2, but now I is 4, and so then the counter becomes 6. In the next iteration, the I value becomes 6, we add it to the counter of 6, and we get 12, and so on. So you can see that I is being added to the previous value of what the counter is currently, but then it's updated every time we run the loop. This notation is very handy, as you can see. We basically created a counter. It kind of keeps track of how many times our loop has run, which is very convenient. Because it's so convenient, this whole notation, which as you know is not the best mathematically because it's not technically equal, there's a whole mathematical sign that people created, and it's called the plus equals sign. So basically, this statement of whatever countup is plus I will be the new value of countup is equivalent to plus equals. You can just say countup plus equals I. Basically, we're going to add I to whatever countup currently is to update the countup value. That's the only difference between these two different loops, and if we execute this loop, you can see that the outputs are the same. So plus equals is a way to update the current value of the counter and revise it every time the loop runs. You can also, plus equals is the most commonly used version of this, but you can use all the other arithmetic. So for example, you can use minus equals instead. If you use minus equals, you can see that the counter, I is being subtracted from the counter with each iteration. You can do a multiply equals, but you can see that it's not a very useful thing to do if you start with 0. If you start with 0, what happens is that because the counter is 0, any I that you multiply it by, it keeps on going back to 0. So you don't see much activity on it. But for example, if you set the counter initially equal to 1, then you can see how every single time it is multiplied by I and it is updated. And you can do also a divide equal. And as you might imagine, dividing by I, with every iteration, you quickly get a decreasing value that gets vanishingly small. So that was a little bit about using plus equals as a counter. So you can use loops as a counter to keep track of how many times it has run. Now that was about a variable outside of the list. Let's learn about creating an empty list outside of a loop and filling it with loop outputs. So as you saw, let's use the same for loop that we used before, range 0 to 12, step 2, I. We have a counter, just like we had before, with plus equals I. What we're going to do instead now is we're going to create empty lists that are outside of the loop. Let's create one called I values. It's initially going to be empty. Nothing is in it, just the empty square brackets like you learned before. And let's create one called countup values. The idea is that using the append function, which you learned before, if you add .append to a list, you can add the element in the parentheses to the list that is specified. Let's add I to our I values with each loop iteration, and let's add the countup values of the counter to the list countup values using append as well. And again, we're going to print I and countup just to make sure that our loop is running. So you can see from print, we can see that the loop did run. We can also see that our counter did work, but we had these lists that we created, and these values should have been appended to the list with each loop iteration. So let's make sure that the lists were working. So if we say print I values, you can see we have a list that contains the values of I, because every time the loop ran, it was appending I to the list I values. And then let's print our list countup values. And it's the same thing. We were appending, after we used the counter, we appended the revised and updated value of the counter to the list countup values. And it worked. So this is a very convenient function that you can use loops for processing to compute and create new values based on I, and then store the outputs into a list outside of the loop. You can also, we've been using the range function up until now, but it's important to know that you can just use any list. The values of I don't necessarily have to be in sequence or having a start or end or a step like the range function. You can just create a list. And then it says for each value in list, it will iterate over the values in sequence of that list. Note here that, remember, the variable that we're using to denote the iterator, it can be anything that you want. So here we call it val. We're saying for val in the list of I values. And we'll just iterate over the list as if it were just indexing right over it. So we can just print. So the I value list was 0, 2, 4, 6, 8, 10, and that's what we get back. And we print back. So we can construct a loop from a list of values, and we can do all the things that we just talked about, processing and storing. And what I mean by processing is that the iterator, I, value, whatever you call it, whether you're iterating over range or if you're iterating over a list, for the same value of I or value, you can do all sorts of different computations. Let's really max out all the mathematical things we could possibly think of. So for example, let's store our values again in a list just to know what the values were. Let's do some math here. We're going to append to the list multiply 2, the value multiplied by 2. To the list of exponent 2 outside of the loop, we're going to append the value to the exponent 2. And remember that the way we denote exponents in Python is with 2 asterisks. And let's create some really big numbers. Let's create a list called exponent val. And to that, we're going to append value to the power of value. We'll print value each time just to make sure that our loop is working. So this list of I values, remember, was 0, 2, 4, 6, 8, 10. But now we have all of these lists, multiply 2, exponent val, and we really want to check that they were being processed correctly. So to check on those lists, we should print them. Let's add some abilities to the print function. You can use, in quotation marks, \n to create a line break for the print function. So you already know if we separate by a comma, that will create a space. So we're going to say the values are, and then we're going to put the list from up here, vowels, so we can see what the list of vowels is. But then we're going to do comma, and we're going to say, in quotation marks, \n. So this will create a line break, so we can actually read some of these outputs. Next, we're going to say val times 2 values are, so multiplied by 2, right? We're going to take the list multiply 2, and then after that comma, we're going to put the list multiply 2, and then again, a line break. And then we're going to say values to the exponent 2 are, and put our list exponent 2. And then we're going to say vowels to the exponent val values are, and we're going to put our exponent val list. And so using this \n, you can see that we get these line breaks, which really helps us read the outputs. So the values are 0, 2, 4, 6, 8, 10. If you multiply those values by 2, they look like this. If you put them to the exponent of 2, they look like this. And if you put them as an exponent of themselves, you get some really huge numbers really quick. So the important thing to know is that if you create these empty lists and then you use the iterating over range or over a list of values, and you mathematically process and use code, you can use these iterators in very creative ways to do some very powerful functionalities in Python. In many ways, loops are really at the heart of programming because we're automating a process to process lots of things quickly and to create very large data sets. So let's look at how we can use the for loop to actually do something mathematically useful. Let's try to calculate the Fibonacci sequence. And so if you remember, the Fibonacci, every number in the Fibonacci sequence is the sum of the two values before it. If we're going to create the Fibonacci series, it's important that we don't create an empty list initially, that we initialize it with two initial values. And the reason is because we need two values in order to compute the next. A lot of people start the Fibonacci sequence with 1, 1, so that the next value would be 2. After that, the next value is 3. After that, the next value is 5. But you can also start the sequence with 0, 1. And because we start with 0 and indexing in Python, maybe this makes sense, and we'll do it this way for this loop. So we have two elements in our list already. We're going to say for I in range 2 to 10. It's important that we start on 2 because 2 is the next element of this series. Remember from indexing that this is index position 0. This is index position 1. And so the next number in the series is index position 2. So we're going to start on the next position of the series, which is 2. The next position of the series will be the sum of these two numbers. So let's create a variable. We're going to call it 2 previous. We want the number that's 2 previous of the current number that we're on. So using indexing, this would be the list of Fibonacci for I, which in the first iteration is going to be 2, remember, minus 2, because we want 2 previous of the positions. So at first, this is going to be position 0, which is exactly what we want it to be. Then we'll create a variable called 1 previous, and it will be I minus 1. With I initiating as 2, if we subtract 1, we're going to have position 1, which is exactly what we want. You can see that it's going to be appropriately for the position we're trying to calculate. These will always give you the 2 previous or the 1 previous values. So when I is equal to 3, this will be 1, and this will be 2, which is exactly what we want. The next value, or the new value of the Fibonacci sequence, will be the 2 previous value plus the 1 previous value. So we create the new value, 2 previous plus 1 previous. We append the new value to the list. Now, when we go to the next value of I, because we have this new value, it will now be the 1 previous. And we'll always, of course, have the 2 previous. We'll add them together again, and we'll append the new value. Spend some time looking over this loop if you're having trouble understanding it. It's using all the concepts of indexing that you've learned before, except that it's doing it with this value of I, and it's modifying the index value by minus 2 or minus 1 so that we can get the previous values, the 2 previous values, to calculate the next value of the series. We add the next value of the series, and our list grows, grows, and grows as I continues to go upward. Again, we always print I just to make sure that the loop is working. We can see that it did work. We wanted to start on the second index position. It does start at 2, and it goes up to, but not including 10, up until 9. We should check the length of our Fibonacci sequence. Let's make sure we got it right. Remember, we start with 2 elements, and then we range from 2 to 10. So this would be 2, 3, 4, 5, 6, 7, 8, 9, which is 8 elements. So 2 plus 8 should be 10. The length of our Fibonacci sequence should be 10, and it is. And finally, let's check the Fibonacci sequence. So this was the element that we first started on. 1 is the sum of 0 and 1. 2 is the sum of 1 and 1. 3 is the sum of 1 and 2. 5 is the sum of 2 and 3. 8 is the sum of 3 and 5. So it looks like it is working. I want to point out that you can always make your code more efficient, but sometimes it helps to really write out every single step first, and then after writing out every single step, then go back and try to see if you can make it more efficient. So, for example, I'll do some cut and pasting to show you how this works. We have 2 previous is equal to this, 1 previous is equal to that, and new value is equal to 2 previous plus 1 previous. We could just take out 2 previous and replace it here, and we can replace 1 previous and replace it here, so that we're calculating both of these as we calculate the new value. But then you can see that we're just appending the new value to the Fibonacci sequence. So we could just put the new value into the append function to append directly to the Fibonacci sequence. So that was before, but after we make the loop more efficient, you can see that we've reduced everything to just one line of code. So we can execute, and we can see, do we get the same result? And we do. We get the Fibonacci sequence back, and you can see we were just replacing the variables and reducing the lines in our code. But you can always write out each step, and sometimes that really helps a lot to try to figure out your way through code. So that's all about for loops. Let's learn about one other major loop style today, which is the while loop, which is very much related to a counter. A while loop should be read. You can read a for loop and it kind of makes sense as you use language. You can also use while is used in the same way. And it's basically saying while a value, let's call it counter, is less than 25, run the loop. So a while loop continues while the condition is true. Almost always a while loop has a Boolean statement. A Boolean statement is a mathematical statement that is either true or false. There's no in between. So these are very useful, especially because a while loop will run while the condition is true. So if we use our counter, for example, let's set the counter initially equal to 2, right? Because we're going to initialize a Fibonacci list with 2 elements because we need to calculate the third. And this is index position 0, index position 1, and then we have index position 2. So we're going to start the counter at 2. We're going to use that one line of code that we just saw and we have been using to calculate the Fibonacci sequence. And then when we're done, we're going to use plus equals to make the counter go to 3. And then we're going to run the loop again, calculate the code, append the next element to Fibonacci. The counter goes up by 1 again. Eventually, the counter will equal 25. And when it's 25, it will no longer be true that counter is less than 25. And when that happens, the counter will not proceed further. So we can execute this, and we can check the length of our Fibonacci sequence that we produced. Remember, we have the first 2 elements, and then we're going up to, but not including 25, which seems like it's 24, but remember we're starting on index position 0. So going between 0 and 24, there should be 25 elements, and that's the case. And if we print out our Fibonacci sequence with 25 elements, you can see again we get the Fibonacci sequence back. 1 is the sum of 0 and 1, 2 is the sum of 1 and 1, 3 is the sum of 1 and 2, 5 is the sum of 2 and 3, and 8 is the sum of 3 and 5. So what did we learn about today? We learned how to use the range function and how it produces a series of integers that we iterate over in a for loop, how to write a for loop, how to use a plus equals sign as a counter, how to create empty lists outside of loops and fill them with loop outputs, how to use a for loop to calculate the Fibonacci sequence. And this will be very important in this lesson and the next activity, where you'll be calculating the golden angle yourself and using it to model sunflower growth. And we learned how to write a while loop using a counter. The plant learning objectives are actually to set us up for this lesson and the next activity. You'll see that in a way, plants are really computers too. They're producing iterative outputs like leaves and flowers, just like the loops we made. Modeling tries to recapitulate phenomena in nature, and no model is perfect. But as you'll see in this lesson and the next activity, that just as a plant iteratively puts out leaves with the golden angle, kind of intrinsically calculating the Fibonacci sequence based on computational mathematics, we'll be doing the same. And that's a type of modeling, trying to look at the underlying math of something to try to recapitulate, even if imperfectly, a phenomenon in nature. So that's all for this video. Thank you for listening.